Hello, I'm Schulte from ETH Zürich, and I will present my joint work with Estril Kushold on reconstruction of convex bodies from moments. Here in the title slide, you can see an example of a convex body. It's a special one, namely a convex body of constant width, and its reconstruction by the algorithm which I will present. So let me formulate the problem. We are interested in the reconstruction of a planar convex body K that is a compact convex set with non-empty interior from finitely many geometric moments denoted by μij of K, where I and j are the exponents of a polynomial we integrate over. And we assume that I and j are smaller equal than some integer capital N. Examples are the reconstruction of a square, a half disk, or a body of constant width like the one in the title slide. This problem is interesting because it has applications, for example, in tomography. It is namely equivalent to the reconstruction from finitely many X-ray projections, but also applications in statistics, signal processing, or image processing. Let me briefly give you an overview of the state of the art. For this, we switch to a more general setting of arbitrary dimension n. Then a geometric moment is denoted by mu alpha of k with a multi-index alpha, and the exponents of the integrand are alpha 1 to alpha n. The order of a moment is just the sum of the elements of alpha. It is known that the moment of order 0 is just a volume of k, and the moments up to order 1 determine the center of mass of k, that is the location information. The moments up to order 2 give us an upper bound for the diameter of k, and the whole sequence of moments determines the convex body k unically. Now, what is known with respect to reconstruction? For triangles in the plane, it's known that moments up to order 3 are sufficient to determine them unically. For arbitrary polygons with m vertices, it's known that moments up to order 2 and minus 3 are sufficient. We are interested in more general questions. So at first we ask for which convex bodies are uniquely determined by finitely many moments. And then can we reconstruct a convex body at least approximately from a finite sequence of moments? And is this reconstruction consistent if the moments are noisy? With respect to uniqueness, we obtain the following corollary from a more general result by Putina. If a convex body K is a positivity set of a polynomial with degree n, then it's also uniquely determined by the geometric moments up to order n. An example is an ellipsoid, which is a positivity set of a polynomial with degree 2 and therefore determined by moments up to order 2. Another example is the body of constant width from the title slide. It is a positivity set of a polynomial with degree 8 and thus determined uniquely by moments up to order 8. More generally, we can even show that those convex bodies which are uniquely determined by finitely many moments form a dense set within all convex bodies. Now let's switch to the problem of reconstruction, and for this we consider the setting of planar convex bodies in the unit square. But observe that the setting could be generalized by scaling. We obtain the following stability result, which gives an upper bound of the Nicodemus distance of two convex bodies K and L in terms of the L2 distance of the geometric moments of K and L up to order n. This stability result is in fact not very good because it contains a factor here which grows exponentially in the order n up to which the moments are given. But by inspecting the proof of this result, we come to the conclusion that it's of advantage to switch to another set of moments, namely Legendre moments, which are formed using orthonormal polynomials. And then the stability result is much better, and we obtain an upper bound on the Nicodim distance between two convex bodies K and L in terms of the L2 distance of the Legendre moments of K and L. And it decreases in the order up to which the moments are known, like 1/n. And therefore, we suggest an algorithm which uses as input possibly noisy Legendre moments and angles, which give us the autonomial direction of the reconstruction polytopes. The output are the support function values in these autonomial directions and the polytope, which has at most n vertices. The reconstruction polytope is obtained by least squares estimation. That means that we reformulate our problem as an optimization problem. With respect to convergence, we can show that if the autonomial directions form a suitably dense set, then the reconstruction polytope will converge to the true convex body. And if the moments are noisy, and we assume Gaussian noise with variance which decreases sufficiently fast in the order of the moments, then we can also show almost sure convergence. Finally, let me show some reconstruction examples. I show you reconstructions from geometric moments which are noisy and also from Legendre moments which are noisy. And the first example is the reconstruction of the body of constant width from the title slide. Here you can see that the reconstruction is quite good. So if, for example, here in the lower right corner, we are given moments up to order 5. But if the moments are only known up to order 3, convergence is not yet reached. Now let's consider the reconstruction from noisy Legendre moments. Here the convergence is faster. As you can see already by reconstruction from moments up to order 3, we obtain a very nice result. Let me show you a more difficult example, the reconstruction of a half disk from noisy geometric moments. You can see that it does not converge here. If we consider the reconstruction from noisy Legendre moments in comparison, we can see that the convergence is much better. For more details, please refer to our article, Reconstruction of Convex Bodies from Moments, which is about to appear in Discrete and Computational Geometry. Thank you for your attention.